Hi, and welcome to the content material for Class 10 of Engineering Statics. You should be watching this video before your 10th class. In this lesson, we will learn how to replace a system of forces and couple moments with an equivalent system. So imagine you are holding a stick, and a force F is acting on the end of that stick. Well, this force pushes downward on the stick, but it also creates a moment where you are holding the stick. The magnitude of that moment is F times d. So the longer the distance, the more the moment that you would feel trying to turn where you're holding on the wrist. If we applied a force F at the location of the hand and also a moment equal to F times d, this system is equivalent to the first one. So we see that this force and moment is equal to this force that is applied at this distance. So a system is equivalent if the external effects that it produces on the body are the same as the original force and couple moment system. Normally, you might be asked to replace the system of forces with an equivalent system at a point, such as point O. And the procedure goes like this. First, find the resultant force from all the forces. Usually, you will find the resultant force components, so the x, y, and z components separately. Next, you will find the resultant moment about the point O, or about the point that you're targeting. The resultant moment about the point O is found by summing up all of the moments created about the point O from all the forces, plus any moments that are applied to the original system. So we see that after following this procedure, we can create an equivalent system in which the force is the sum of all the forces plus the moment that is created from all of the original forces. And this system is equivalent, in terms of its effects, to the original system. So for example, these traffic lights exert a force on the pole. So if we want to find the equivalent system, first we add up the two weights, W1 and W2, to find the resultant weight, WR. Then we find the moment caused by each of the two traffic lights about the point O. So these two systems on the left and right are equivalent systems. So let's look at some examples of how to do this. So in this first example, we see that there is a force acting on this beam, and we want to find the equivalent system, same force and moment that is equivalent to what we see here about the point O. So we know that in any case an equivalent system is that the resultant force is equal to the sum of the forces, and that the resultant moment about the point that we choose, point O, is equal to the sum of the moments about O. Well, the sum of the forces is quite easy. There's only one force. So what we'll do is we'll break up that force into two components. It's x and y components. So here is the point O, and here is the point at which the force acts. So what we see is that we have the x component of the force, we have the y component of the force, and we have some distance here. So we know this distance is 0.06 meters, and this one is 0.18 meters. So we just need to know what the forces x and y are. Well, we're given a triangle here, so we know that the force x is equal to 4 over 5 times the force, which we're told is equal to 8,000 newtons. so 6,400 newtons. For y, it's 3 over 5, so that's 4,800 newtons. So at this point, we'll find the moment. So the sum of the moments, and we'll say that this direction is positive, is first that the force of the x acts this way, so it's negative. So force of the x goes counterclockwise, so negative times the force of the x, which is 6,400 newtons, times the perpendicular distance, which we see is 0.06 meters. Now plus, because the force in the y acts in the positive direction. So the force in the xy times the perpendicular distance, which we see is 0.18 meters. So plug that in, we find that we have a positive moment. So the moment, the equivalent moment about the point O is equal to 480 Newton meters in the clockwise direction. And the x component we know already. So this system is equivalent to what is drawn above. In our second example, we again want to find the equivalent system. This time we have multiple forces acting, so we do need to add up all the forces. We know that the resultant force vector is equal to the sum of all the forces, and we can break that into the x and y components. So let's start with x. So the resultant force in the x direction is the sum of all the x forces. So we see that there's 40 Newton force acting in the positive direction, and there's an x component acting in the negative direction. So we see that we'll take 40 newtons minus just the x component in this one. So we see that's 3 over 5 times the 60 Newton force is equal to, in this case, 4 newtons. So there's a 4 Newton force equivalent acting in the positive x direction. In the y component, we see that there is one force acting down. It has a magnitude of 30 newtons, and another force, again, the y component of that force. So both of these act in the negative direction. So we have negative 30 newtons minus the y component. That's 4 over 5 times the 60 newtons. When we do that, we find that's negative 78 newtons. So the next thing we want to do is we want to find the equivalent moment. So first thing we have to notice is that some forces don't create any moment. So for example, the force on the top acts through the point O. So this force has no moment up top. So we can ignore this one. However, we do need to look at the other forces. First, we see that there is this force over here, and there's a y component and an x component. Notice carefully that there is a small distance here of 0.4 meters. And the other force that we have to consider is this force, which goes in the negative, goes to 40 newtons. So we're going to call counterclockwise positive, and we're looking for the resultant moment, which is equal to the sum of all moments about the point O. So we have 3 to add up. We have 2 positive and one negative, according to what we call positive. First, let's do the positives. So we see that the x component times the distance. Well, what's the distance? This distance is 2 meters, and this distance is 5 meters. The x times the 5 meter distance plus Fy times that distance, which is 0.4, plus the negative moment, which is the 40 Newton force times the 2 meter distance. So let's start putting these numbers in. Okay, when I plug these numbers in, I find that it's a positive 119 Newton meters, which means it goes in the counterclockwise direction. Now we can also find the resultant force magnitude, which would be comprised of both the x and the y components. We can find out the direction that it acts. So the angle be equal to the inverse tangent of the y over the x. If we were to call the angle like this, so if I call this angle like this, FR, this is FRY, and this is FRX. So when we put those numbers in, we find that that angle, theta right here, is equal to 87.1 degrees. So we can draw our final diagram like this. This equivalent system about the point O has a force acting with this angle theta equal to 87.1 degrees with a magnitude of 78.1 newtons and a moment in the counterclockwise direction equal to 119 Newton meters.